Did you hear that?
Yeah. Okay. Welcome, everybody. Welcome to the CSCA48 final review seminar for winter 2022. I'm just going to post a link to the Google Slides if you guys want to follow along. And let me start sharing my screen. All right, can everybody see? Hopefully. Awesome. Okay. All right, welcome everybody. So today we will be going through these sorts of topics. So I'm going to go through several different types of trees. Just get the basics down. We're also going to go through big O notation, bit of time complexity, and then BST specifically, we're going to do a lot of examples on because that's one of the biggest parts of your entire course. And then I'll go through sorting. You've got 3 different types of traversals. And then I'll hand it over to Tabeb. He will go over recursion, graphs, DFS, BFS, and then object-oriented programming as well. Yeah. Oh, right. Okay. How do we want to do this? Do we want to do it? How do we want to do this? I guess if yeah, BSTs are the biggest one. No, it's still not working. Or is this good?
It's like it's cutting off the T in topics right now. That's what it is.
Tabeb, do you have any suggestions? Because a lot of mine rely on like animations
I
and stuff.
think it's fine. Oh no, you have to. How did you fix this before? Do you remember?
I forget. Is there a way to like share half of it? Let me see.
You're just sharing. I think you're just sharing like Chrome, right? So can you share like your whole screen instead?
Yeah. 1 second. Oh, the scaling. Okay, where's that? Okay, what if I do this then? Is this good?
Yeah, that's it.
Okay, awesome. Okay. I can't really see the chat. I'll try to respond, but Tabib's going to be going over it mostly. Awesome. Okay, so first thing we want to go through are the different comparisons between trees. Okay, so can anybody tell me, like, what is a general tree? And I don't mean the ones outside. Like, what's the difference between a general tree and a binary tree?
A general tree is just a graph with no cycles, and a binary tree is a tree where every node has at most 2 children.
Exactly. Perfect. So general tree has like unlimited amount of children nodes, right? BST or BT at least can only have 2. It's also unorganized, so that'll be coming up a little bit differently, and it's also unbalanced. It can be balanced, but typically we try to We don't try to assume that's balanced. So for binary tree, you got it. It's also max 2 children nodes. But the difference between a binary tree and a BST, a binary search tree, does anybody know?
Between a binary tree and a binary search tree, wouldn't it be the fact that it's organized like greatest and smallest?
Perfect. Yeah. So on the left side of every node, like the left child, it has to be less. So it still can't have more than 2 children nodes, but it's organized. Instead of a binary tree, there's no rules as to how to add the nodes. So it can be in random order. But for a BST, left node is less than the current node is less than the right node. And I didn't include the equal sign here because depending on who you are, or like who you talk to, you can have it either on the left or right if it's equal to the current node, or you cannot have any duplicate nodes. But yeah, that's why I excluded it. And what's the difference between a BST in general and a balanced BST?
Balanced BSTs, any 2 leaf nodes have at most a height of 1 apart, I think.
Kind of. Yeah. So a balanced BST, it means that we have it. Yeah, the subtrees should be equivalent on both sides. So for a regular BST, we can technically consider like a linked list. It'll look like a linked list, but it'll have left and right. But the time complexity will be ON. So continuing all the way down. So for a balanced BST, the height is log n. Yeah, so we are going to go through a balanced tree. So we'll go through it in a little bit, like after this slide. I'll show you the difference between the two. I think for the BST, I wrote this one incorrectly, but for general tree, it's going to be ON in worst case scenario. Can anybody guess for binary tree as well?
Login, I guess.
Close, but not login.
Should be
It'll
an
be
log.
It'll be ON still.
Oh, it's not balanced.
No. So that's what I'm trying to, sorry. So the other 3, they're going to be unbalanced. The only one that's balanced is the last one. Yeah, so this one should also be ON. BST, if it, like on average, it'll be log n. And yeah, the difference between general tree and binary tree, they're not really sorted. So general tree, it still has, like it can have several different children nodes, whereas a binary tree can only have 2, but they're still not sorted. For BST, I believe this should be ON. Sorry, I will change that. But the last one will be O log n. Yeah, let me just change this. Yeah.
Wait, are these the worst case complexities for searching?
Yes. Yeah, so worst case scenario, binary search tree just looks like a linked list, but it has 2 nodes in it. Exactly 2 children nodes. If you're searching for one, yeah, searching instead. Yeah.
When we refer to time complexities, we usually refer to the average big O notation, right?
Yes. In this case, I am referring to the worst one right now. Sorry. Yeah, okay. So basically for worst case scenario, a general tree can look like a linked list. So it's going to continue on. Here, I'll show you an example. So this is a general tree. It can have several nodes, it can have, or several children, it can have one child, it can have 0. But worst case scenario is it's all going along the one side, which means it looks like a linked list. So if you're searching and it's the worst case scenario, it's going to be ON because it's going to be at the very end. And even if you wanted the average big O notation or time complexity, it's going to be n divided by 2. And remember, we factor out different constants instead. Does that make sense? Yeah? Okay. So yeah, difference between general tree, binary tree. Binary tree can only have up to 2 children nodes. Yeah, this is an example of a balanced binary tree, but it doesn't have to look like this. So for here, here's an example of the 2 of them. So can anybody tell me which one's the binary tree, which one's the binary search tree?
On the right is the binary tree. On the left is the BST.
Perfect. Yeah. And can anybody tell me why?
Because the left subtree of the 2 is 7, which is not smaller or equal to 2.
Yeah, awesome. So here's kind of an example just to figure out the difference. This is based on a previous question on last year's A48 final exam. So just make sure you know the difference between trees, binary search trees, balanced binary search trees, and the difference between unbalanced and balanced. Here's an example of the balanced tree versus an unbalanced tree. So over here, you can see like technically the bottom one is still a BST because it has at most 2 children nodes, but it looks like a linked list and it has the time complexity of it. Yeah. Any questions so far?
So for balance, does it just have to be that the height of both sides is equal, or is there some extra requirements for it to be balanced?
I think it can contain 1 child so long as it's equal. Tabeb, can you confirm that?
It depends on the tree. There's different types of balanced binary search trees like that have different sort of properties on like what is considered balanced, and you'll learn about it in B63. There's like AVL trees, height balancing trees, red-black trees. Like they all have different different ways of saying that they're balanced, basically. So there's
or
no
like, for
explicit.
example, in this one, let's say you remove 85 so that the left has more than the right. Is it still balanced? Like, yeah, does each level have to be full?
Not necessarily, no. In most balanced binary search trees, again, it depends on the type of balanced binary search tree. It doesn't have to be like a perfect full binary search tree.
Okay.
Like
got
there
it,
are even binary search trees where like they accept like the left side can be half as full as the right side. So like,
Okay.
it really depends.
Okay, thanks.
Yeah.
Sorry, in this course, it's going to be specified on the exam, like the criteria for the balance tree, since you said there's different types.
Yeah. He'll explain like for balanced or unbalanced, it'll be pretty obvious. You'll go, like Tabeb said, more in detail in B63, but for now, they're pretty obvious in between the 2 of them. Yeah. So time complexity, as you can guess, balanced BST, the height is log n. So for searching, it's going to be the same time complexity, way better than the unbalanced by BST. Yeah, Caitlin, I think that's correct. When we're talking about balance, we mean symmetrical. It's not always symmetrical, but it's mostly filled in. Not by the data inside of them. Yeah. So I have a couple questions for us to go through. So apparently you guys have done this one. What's fun about this is when I was taking this course, this was one of my assignments. So I didn't know if you guys had gone through it. But I'll give you guys a few minutes, maybe 5 minutes for this one. Try to implement a function that initializes this new music node. So you're given frequency, bar, index, and here's the struct over here. Yeah. So try to come up with a function for it. Give you a few minutes for that. Okay. So I think that's about enough time. So like in the chat, you can kind of see a couple people answering. So yep, first thing you want to do, initialize it to null, create a new one. Yeah, a lot of people are texting, that's good. You want to create the new space. Remember, important difference for this one is that when you're first writing it out, make sure it's the pointer. And then when it's actually looking at the size, make sure the size is for the music note, not a pointer of the music note. We do have to set it to null because otherwise, actually, I think it's good for like checking later. You don't know what's going to be in it when you first initialize it. So I think it's good practice. Although I think calloc does return it, like initialize it to null.
Is this just calloc cannot assign memory?
I think so, yeah. If it's completely filled up, I think it does return null still. But you just want to be careful, right? Yeah. Yeah, so make sure you return it.
Can we write the first line and second line into one line to save spaces? Sometimes we have line limit.
Sorry, for which one?
Can we write the first line and the second line into one line?
Oh yeah, I guess you can. Yeah, you can.
Thank you.
Yeah, you should be able to. You wouldn't lose marks on it. Yeah. Okay, next one. Initialize all the values. You guys know this. Make sure left and right are null. Otherwise, it'll have garbage in it, and that could cause a lot of problems. Calloc does initialize it to 0. Malloc does not. So just be careful. I don't think it's /0. Yeah. And then last but not least, we're going to return the new music note if it's not empty. Next one, we're going to go through inserting a music note. Don't worry, we're going to do this one, we're going to do insert and search. And then we'll go on to another example, which I'm pretty sure you guys haven't gone through. It's with quads. Yep, so I'll give a couple minutes on this one. Yeah. So since the key is unique, that's the one you want to sort by. Also for these questions, try not to go back to your notes because we are going to go through one that's new and it's good to practice again. Yeah, awesome. Okay, yeah. So going through it, if no root exists, no head is there, you want to return the new node, you're creating a new BST. Duplicate music notes. Yeah, I probably should have specified this. But recall back, we wanted to print out that there was a duplicate, and we wanted to return the root, so we didn't want to insert it.
Won't this crash if new node is null?
Pardon?
If new node is null, then when we try to access key from new node, it will just crash.
Segfault.
Right?
Um,
So shouldn't we also check that new node is not null?
yes, we should. Yes, sorry. At the beginning, yeah. Yeah. Yeah, I'm not sure whether or not it was a precondition that new node is not null, but that's a good point. Yeah, make sure that you check if new node is null as well. Yeah. Next thing we want to do, we want to go down the left or right. For this one, I actually did if it's equal to, or actually it won't be equal. If it's less than, we go down the left side. If it's down the right, it's down the right side. And at the end, don't forget to return root. Otherwise, you're gonna miss a lot.
But in this case, what if we have a situation that the new nodes, it has the equal value, but according to BST's definition, it should go to the left subtree. But in this case, since the else is used, it will go to the right subtree.
If it has, oh, no, if it's equal, we don't want to add a new duplicate in music note.
Oh, okay.
So we wouldn't actually insert it at all. That's why it's okay that we're not checking the equals case down below, because if it's equal, we're just going to return the root. Yeah, remember the key has to be unique, so we don't want to add duplicates. Any questions? We're good so far? And yeah, the right is not redundant for the else, because if we did, we only want to do one or the other. Otherwise, the BST might not be a BST, it would be a BT. Yeah. Okay, same example. I created an extra function though. So the search function, usually on bar and index, I want you to try to go through that one. And then if you finish that one soon, go through the frequency instead. It'll be relatively the same, but a couple differences. For Mario's question, for the first note, is the first music note that you find. Yeah. And technically, since it's like it's organized by key, which is by the index and the bar, it should be the first note that's played with that specific frequency. Okay, so kind of this is already a review. So the first one, yeah, so you want to check whether or not it's empty. If it's not, or if it's not found, since we're using recursion during this, it can either be that the entire thing's empty or you just haven't been able to find it. So yeah, we create a temporary key. Remember, equation is 10 times bar plus index. If we found it, we just want to return the actual music note that it's at. If we haven't, we go down the left side, recursion, and that's why if root is equal to null, then it can be either you look down like a leaf node and then it had no children, which means that you couldn't find it. Otherwise, search down the right side. And I'm not sure, so I have a lot to go through. I'm gonna try to go kind of through the solutions. You can try coding along, it might go a little bit faster. If we don't get to everything, don't worry, I'm gonna stay behind for quite a bit if anybody has any questions. And Sean, yes. Here, technically the else is redundant because it's a return statement. Yeah, it does make it clear.
Recording in progress.
Okay. So kind of the same thing with the frequency. If it's empty, return it. If you found the first one, so that's what I mean. Like once you find it, it's just going to start returning it. So you don't really have to worry about like looking for the second one or the last one. You search down the left one, you search down the right one. That should say down the right one instead. But yeah. The BST is not sorted by frequency. So it'd be sorted by key. That's why I said for the first one that you can find with the frequency. Yeah.
Doesn't it look like we're assuming it's sorted by frequency in the second one?
We are, yeah, it does look like we are, but we're actually just searching for the first frequency that we can find based on the.
Wait, could you not have the case where it looks down the left side of the tree and then reaches the end and then just returns all the way up? No. Because if we reach the very end of the leftmost subtree, then we'll return null if we don't find it. And so then would it just return null all the way up?
Oh, I know what you mean. I think. Oh yeah, okay, yeah. Might not have been the best example. Yeah. You might have, yeah. Yeah, I kind of understand that. Yeah. So in this case, technically the BST would have to be sorted by the frequency. So you can check the entire thing and make sure that's sorted properly. Yeah, so this one instead, you would have to do, yeah, an in order search. Yeah. Yeah, that's my fault. You would have to go through all of them. Because technically frequency is not. Sorry about that, yeah. Yeah, it would be ON. Yeah, sorry. I can go through this again later. But yeah, this would be an in order instead. Yeah. Okay, so this is a quad. A quad is basically you're given an image and it's a quadrant specified by the position of the top leftmost pixel and the width of a height of an image. So this entire image is made up of these quadrants. And we have all of these different values, so to speak. And then we've got left and right. So for this one, it's going to be initializing a new quad. It's going to be very similar to the same way that you've been doing it before, but just for practice, make sure that you're initializing all of them. Make sure you're initializing the left and the right to null. Yeah, and it's the same thing, same method, right? You want to make space for the pointer. Make sure you initialize it to null. Although I think calloc already returns it to 0. If it is null, return new quad. Then you want to initialize all the values. This is a more practical one. The music one was as well, but this is another version of what you can do. And then last but not least, you want to return that new quad. Does anybody have any questions? I feel like this is pretty similar to what we've already gone through. I think calloc, Tabeb, correct me if I'm wrong, but calloc does return null if there's not enough space. So
Yeah.
yes, you should be able to, thank you. You should be able to just do quad, new quad, and then you can just start with that quad. Yeah. Yeah, just that one line, yeah. Should be good, okay. Same thing again, we're gonna go through insertion. So in this case, the key is now based on tx plus ty times sx. So sx is the actual width, like the original width of the image, should be constant. And then tx and ty are specific to each quad. So that's the position of the top leftmost pixel in the quadrant, which is why it should be unique. Just kind of going through this. Yeah, so if it's empty, you want to make sure, remember, if it's equal to null, just return the new node. If we found a duplicate, we want to return it again. I'm not sure what that means. Otherwise, we're going down the left or right side. Does anybody have any questions? I think like this is relatively making sense to everybody. Yeah, okay. Okay. Let me know if I'm going too fast. I know I'm speeding up a little bit. So for this one, make sure you're trying to search through tx and ty. Remember, sx is constant throughout all of them. That's why they don't actually pass it through. SX is technically not global. It should be the same for each one though. Yeah. Yeah, you can pull it out of root. You can pull it out of anyone. Yeah. If the root isn't empty. Thank you, Joseph. I think Tabeb will be going over recursion later on. He might cover that. So for this one, yeah, I kind of just had it all together. If it's null, return null, because you can't find it. You want to first set up that first unique key to search for. If you found it, return it. Otherwise, keep searching for it until it either returns null or it is null, or it returns the actual one. You do have to use recursion for these ones, I believe. That might be one of the requirements. On the exam, it'll say whether or not you're supposed to use recursion. Yeah, if you do it iteratively, it takes up a lot more space and it can get quite ugly. Yeah. Okay, so for this one, try to find the successor of the quad. So remember, it's passed through the right child, and then you want to keep going down the left side until you either you find that it's null. There's no left side. Yeah. Yeah, so Arub did it without, or with iterations without recursion. That would technically work, yes. Kind of what you learned as well during linked lists, right? Now try doing it with recursion. No, you don't have to check whether or not it has a right side or a right child because the left side will be less than the right side. Yeah, okay. Yeah. You guys got this. Okay. So if it's not equal, you don't have anything. But you're checking every time whether or not the left side is equal to null, then you have found the right child. Yeah, if you have found it, great, return it. Otherwise, you want to keep searching down it. Yeah. Yeah, I see a lot of great answers in the chat, so yeah. Okay. So deletion. This one is big. I encourage you guys to try it out. It gets quite long. But it's really good to practice because especially that 2 children case, it can get quite difficult and sometimes you can have a blank on a midterm or a final exam, which is worth like 50% of your mark. So make sure you practice. Does anybody know the 4 cases off the top of your head?
Is it 0, 1, 2 children and child doesn't exist, maybe?
You're close, yeah. Technically, yeah, okay. Technically, I said like the separate, like each child is its separate case. But yes, you're right.
Or would or would empty root be a case?
Empty root would also be a case. You would have to check that. Yeah.
Would it be the fifth case, or is it part of the 4 that you had thought of in the slide?
So I consider left and right to be separate because you have to, like, the temporary one will be separate.
Oh, yeah, gotcha.
Yeah, if you say like left and right are the same, technically that's not true because they have different cases on what you can do. Yeah, I think you guys have got this though. So yeah, you create a temporary key. If you can't find it, that is one of the cases, Sean. Return null.
Haven't
If
you
it
just tried
is
to access root as x, like root as x before checking if root is null?
right, yeah, sorry. So these should be switched. Thank you. Yeah. Yeah, okay. So yeah, like Ethan specified, you'd want to switch root to be switched, and then you make the temporary key. Yeah. So first case, if there's no children, what do you do? Yeah, make a reasonable assumption. That's it. That's the entire review seminar. Just make a reasonable assumption. Yeah. Okay. Free the root. Yeah, and return null. Yeah. Awesome. Okay. What about with the right child? What would you do? If you're not saying a reasonable assumption, you're doing it wrong.
Make attempt to hold the right child and then free this thing and return the right child. Return the temp.
Yeah. Yeah. Awesome. Perfect. Yeah. And so this is just, sorry, this is a continuation. So yeah, we have the left side, it's null. So we do the right side, we free it, then we return temp. If we free root before this, we don't have access to the right side and we lost a ton of the BST. So as you can probably guess, if there's a left child, you do the exact same thing. So you hold on to the left side. All right, what if there's 2 children? This one's kind of tricky. Yeah, so first find this successor. Yeah, that's perfect. What do you mean by swap? Yeah, okay, so copy the successor. Yeah, copy all the data. Want to free the successor. How are we going to do that?
Call delete on it from this root.
Perfect. Yeah. So call the BST delete. We literally have this function for a reason. We go down the right side, we try to find it, and then we return the root. Yeah. Any questions? Good. Hopefully. You guys got that one, so that was really good. Okay. This is for deleting the entire, oh, yeah. Okay, this is technically still a continuation, sorry. If you don't find the node that you want to delete, you continue searching. You guys know this, you're good. Okay, this is for deleting the entire BST. Now there's a certain order that you have to do this. It's one of the 3 that we're gonna go over later. Tabeb, I also know that you're looking a little worried because I'm going over time. So I will switch to you soon. Yeah.
You're fine. You're fine.
Okay, good. But yeah. So does anybody remember which traversal we should use to delete
There's
this?
a really bad way of doing this. Just do while root does not equal null, delete root from itself. Set root to BST delete root.
Ooh. Ooh, that would.
You'll always be replacing it with its successor until the whole thing is gone. It's just incredibly inefficient.
Okay, well that's another way. Thank you for that. Yeah, so it's post order. So if there's none, return it. Okay, so I'm gonna show you the inefficient way, okay? So there's like, hold on, so there's Ethan's level, then there's this level, and then there's gonna be another level, okay? So this one, we go through each of them, right? The 4 cases. So we're gonna go through no children, 1 child, left child, no children. Technically 5 cases, root is null. Right, and then we return null. That would be specified in the actual function. And yeah, you guys all got it correct. It's post order. What's a more, oh, dang. Where did it go? There is a more efficient way to do this. Or it might be for the sorting traversals, not for deleting. Okay. So we're gonna go through this. What are the 3 sorting traversals? You already got one. You got post order. Post, pre, and perfect. Yeah. So you got in order traversal. What are the different orders? Sorry. Okay. So for in order, which ones do we want to go down? Left, root, right?
Left node, center nodes, and right node.
Perfect. Yeah. Okay. What about for pre-order? Root, left, right. Yeah. Kishi, can you hold your until the end? Okay. Yeah. Sorry, I will get to that afterwards. Sorry. I think that would work. But sorry, I know I just paused. Sorry. Okay. Post order traversal. It's the last one. Left, right, root. Yeah, perfect. Okay. So for this is an example. What would the in order traversal look like?
We'll print out every node in the BST in order from the smallest to the greatest.
Yeah. Perfect. Yeah. From the smallest to the greatest. Okay, what about pre-order traversal? Oh, okay, 1 second. I'll go back to the previous slide. You'll have access to these slides. I'll repost them at the end of this. And I'll also post them in the Emacs server, and Tabeb will post it on Piazza. Yeah, okay. Okay, so we got in order. What's pre-order? If anybody wants to type it out.
I can say it out. That would be 50, 750. Wait. Pre-order, right?
Pre-order, yeah.
That'll be 50, 17, 9, 14, 12, 23, 19,
Yeah, then 76.
76,
Yeah.
54, 72, 67.
Yeah. Yeah. So this one's kind of like pretty zigzaggy, but yeah,
Can we
basically follow down
imagine-
the. Pardon?
Can we imagine that we are pouring the water into this BST with the gravitation on the orientation on the left and up, so that it would like, yeah.
Yeah. Yeah. That's exactly it. Right? That's a really simple way of thinking about pre-order, right? And just think about you always go to the left before you go to the right. But yeah, if you're pouring water from the top, that's a really good way of visualizing it.
A little bit dumb, I just noticed this, but is the prefix before order just referring to where root is located in the order? So in order is root in the center, pre-order is root in the left position, or like first search, as in post order is center is on the right side. Technically, if you just write it left to right.
Yeah, I never thought of that. Yeah. Yeah, I guess
Yeah,
it
that's
is.
how I
Yeah.
remembered it for my midterm.
Yeah, that was awesome. Yeah, just remember that. That's great. Okay, last one, post order traversal. What would this look like?
That'll be 12, 14, 9, 19, 23, 17, 67, 72, 54, 76, 50.
Should be, yes. Yes. Yeah. Yeah. Keeps going from the bottom, goes up. Yeah. Okay. 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 Tabeb, I think I'm gonna go over these afterwards. So there's in order, pre-order, and post-order. I code it through with quad. And then we've got 3 other questions, but I'm gonna skip to Tabeb's one just because I want him to get a chance to speak, and then we'll go over this at the end. Is everybody
Okay.
good with that?
Let's take a 5-minute break. We'll come back at 5:13, and then we'll go over graphs and OOP, and then we'll cover whatever other questions we have left. Okay.
Thanks, Tabeb.
Right. Can you guys see my screen?
Yeah.
All right, cool. So this part, we're just going to go over graphs, different algorithms for graphs, time complexity of graphs in terms of adjacency lists and adjacency matrix implementations. And then we'll just briefly go over object-oriented programming. So I'm just going to go over like some sample questions you could get for object-oriented programming as well. And we'll go through it. So for this part of the review seminar, we aren't going to be doing any coding at all. So if you want, you can get out like a piece of paper. We'll do some like traversals and some other like drawing graph sort of problems. Okay. So let's start with just a quick little review of graphs. So what is a graph? A graph is just a way to model, is a model to represent items and the relationship between the items. So you have this thing called a node or vertex, and these are like the actual items, and they're denoted by this set V. So like you have a set V, and the set V contains like all the possible nodes, like Alice, Bob, Chris, Diana, Eric. These are nodes. And the edges are the actual connections between the nodes, denoted by the set E. So E has the edges. So like, for example, Bob to Eric is an edge. Alice to Bob is an edge, and Bob to Alice is also an edge. Okay, so like the E contains all those edges, and usually you're given, a graph is usually given in the form, you have a set V and a set E. So all the nodes and all the edges. Usually that's how it's given to you, like in a theoretical question. Okay, you can also get the cardinality of V, which is basically like the size of V, and this is basically a way to say the number of nodes, and cardinality of V is a way to say number of edges. So when we're dealing with like big O notation and stuff like that, you'll see this kind of notation. Okay, so for this example, like I already explained a little bit, nodes are the actual people. Edges are whether a person follows another person or not. You can think of it like that. The cardinality of V would be 5, and the cardinality of E would be 6. So like with the bar. Could a graph have directed and non-directed edges like your example? Yeah, it could. And sometimes it could be undirected. Sometimes it could also show like double arrows. That's basically like same thing as saying it's undirected. It's just basically saying that there's a bidirectional, a bidirectional relationship between two nodes. So we'll talk about
Would we
that.
say that the bidirectional edges have two connections then? Would those count as two edges?
Yeah. Yeah. If your graph is directed, you would count that as 2 edges.
So would this one have 8 then? Or is this different if it's both directed and undirected?
So I think this is 6 actually, right? 1, 2, 3, 4. Oh no, yeah, this is 8 actually. Yeah, 8. Yeah, it would be 8 edges. Okay. So like I said, like we talked about, directed edges have a one-way relationship. So Bob, for example, follows Eric, but Eric does not follow Bob. That's why you only have a one-directional arrow here. Undirected edges have a two-way. So Alice follows Bob and Bob follows Alice. So you can represent this in a directed graph with a bidirectional arrow. In an undirected graph, you wouldn't have any. Okay. So let's talk about graph traversals then. So you guys should have seen BFS and DFS. So breadth first search is basically like traversing a graph level by level, and you usually use a queue to be able to do this. And then depth first search is you go down an entire path before you backtrack and go and try to attempt going down other paths. And you can usually use either a stack or you can use recursion to achieve this. Okay, so I want you guys to take a few minutes to just sort of remember how to do BFS and DFS. And you can show one possible traversal that you can do on the following graph. Okay, there are multiple different traversals you can do, obviously. So you can go ahead and try to, you can try to show just one of each of those, and then we'll take it up together. Okay, so I will give you guys like maybe 3 minutes or so. You should be familiar with what stacks or queues are. I think you did have to implement a queue, but they're basically a first in, first out data structure. If you were to implement BFS on a test, would you have to create your own queue? So BFS would use a queue. I highly doubt he's going to ask you to implement BFS on a test, but yeah. I mean, queue can just be a linked list, right? Yeah. I think for your last assignment, you just did it recursively. So you can do DFS recursively. I'm actually not sure if you implemented BFS ever. So if you have never done that, then I don't think you need to know the implementation of BFS, but you should know how it works at least. Yeah. Oh, and I guess I should have said start from S. Sorry. Start from S and then go outwards. So S is like the source node. And you're not particularly looking for anything. You're just giving like what the traversal would be if you went through the entire graph. Okay. Okay, so I think I'll go over it real quick. So my document here. Okay, so let's go over BFS and how that would look like. So in BFS, you have a queue. Okay, so a queue is going to be a first in for first out data structure, and you're going to initially put in your source node. So you're actually going to start from S. Okay, and then let's say this is like your output. So what you're going to do is you're going to, in your loop, you're going to pop your S from the queue or dequeue it from the queue, and you're going to print it out. But then once you've done that, you want to add all the neighbors of S. So let's say S is blue, then you want to add all the neighbors. So that might be H, that might be F, and that might be B. Okay, and that's pretty much all the neighbors of S. So we add H, F, B in the queue. All right. So like it doesn't really matter which order you do it. That's why there's like many different ways, or you can traverse BFS or DFS. So I've just did it in this clockwise order. And so you do that. So these are the neighboring nodes. These are also the nodes that are distance, you can say like 1 from the source as well. So I've highlighted those in red. And then you continue on going from the queue. So from the queue, you always pop what the first item is. So the first item is H. You're going to print that out. And then you're going to add the neighbors of H. And I'm going to highlight these ones in green. So the neighbors of the red nodes. It's going to be A and G. So I'll add G, A. I guess I'll just add AG. Okay. And yeah, that's pretty much it. H doesn't have any other neighbors, so so S is technically a neighbor of H, but since we've already visited S, we don't visit that again. So we're done with H. Then we want to go to F. We want to pop that and print that out, and then try to add the neighbors of F. So G we've already explored, or we already added to the Q, so we're not going to add G to the Q again. But we're going to add E. Okay. And that's pretty much it. Again, S we don't add because we've already visited. So yeah. It doesn't really matter, no. There are multiple ways to traverse BFS, so yeah, the order in which you pick them don't really matter. Yeah. And so then we continue on with B. Okay, so we add the children of B, or sorry, the neighbors of B, and we only have one that we can possibly add, which is C. S is obviously already visited, so that's fine. And then we're finally onto the green nodes. So we're at A now. We're gonna DQ A. We see that A doesn't have any neighbors that we can add that are new because we visited H already, we visited B already, so we don't add anything. And then we go to G, we DQ G, we print that. We see that there are no neighbors we can add, so it's just gonna be done there. And then we DQ E, okay? Yeah, E, so E is going to have one neighbor here that we didn't add yet, so we add that. So I can highlight this in blue. And so we can add that to the queue. Okay, sure, I'll make this blue as well. Oops. Okay, and so we're done with E, but then of course we go in order, like how we add it to the queue. So we pop C or DQC and print it. C, of course, we don't add B because we've already visited. We don't add D because we're already going to visit it. So we're just done there. And and then finally we're just going to DQ D, and of course everything has already been visited. So that's basically one way you can do breadth first search on this this graph. Okay, and what you see is like the node that is marked in dark blue, it's basically distance 0. The node that is marked in red is distance 1. Or sorry, distance 1. And the nodes that are marked in green are distance 2. And the light blue is going to be distance 3. So you can use this to easily compute, like you can go like by level, go through all the distance 1 nodes, then the distance 2 nodes, and then distance 3 nodes. So you have that sort of behavior. So does that make sense to everyone? And of course, you can have like multiple orders. Like you could have gone BHF first. You could have gone like GA instead of AG. So yeah, there's many orders you can do this. Okay, so now let's do BFS. So DFS is actually simpler to implement in code because you can just use recursion. Wouldn't the order have to be consistent though? Yeah, not necessarily, no. In a question, he might ask you specifically to do something in like clockwise order or something. But yeah, if we only want to do till distance 2, how do we do using the queue? If you only want to do until distance 2, you can have like a distance variable, right? Set it to equal to 0, and then so basically when you so like I think I'll talk about this later actually, but you can actually go level by level, and like you can basically like take the size of the queue, add all the children up to the size of the queue, and then you have size of the queue is equal to 3. So you can add the children for like these 3 nodes, and then you know that these neighbors are the neighbors for these 3 nodes. So that's when you know to stop. I can talk about it later. It's a little bit gets into implementation details, but you can actually decide when you want to cut off, which distance you want to cut off to. But yeah, I can talk about that later if we have time. Okay, so let's talk about DFS. So for DFS, you can do it recursively. So if you do it recursively, you implicitly use a stack. So a stack is like a last in, first out data structure, right? So like if you have ABC in your stack, and if you do stack.pop, it will give you C, right? Like the last item. Whereas with Q, we were always popping the first item. That's basically the only difference. And you can use linked lists to like implement both of these if you ever need to. But yeah, the way the stack is going to work. So let's say we start again from S again. We're going to put S into our stack, and then we're going to output S into our stack. Or sorry, we're going to output S. Okay. And then the way DFS is going to work is I'm going to explore one path until I can no longer explore the path, and then I'm going to backtrack and check the other paths. So what that means is like S has like 3 possible neighbors it can go to. I'm going to pick one. I'm just going to try to go as far as I can. So let's say I'm going to pick H. Okay, I'm going to pick H. So that's when I put S into the stack, because I put S into the stack because I want to explore the other paths from S later. Okay. I would say I would say you don't need to know how to code BFS DFS. Just because like in past exams, I can't really find coding questions for graphs, but like since you guys did have an assignment on graphs, I would say at least be able to understand how to code DFS like recursively. I think that should be a good thing to go over. Okay. So basically you go to H and then you output H. So now you want to go through the paths for H. So let's say you can go to like A, for example. Okay, so when you decide to go to A, you have to put H into the stack. Okay, and then you output A, and then you see, okay, I can't go further into A, so I'm basically done with A. I'm going to go back, and I'm going to go back to H. Okay, so now I'm back to H. Now I'm going to try to go go to the other neighbors of H. So the other neighbors of H is just G and S. S we've already visited, so we're going to go to G. Okay, so H is still in the stack. Now we're going to print G. Okay, now I'm going to go down the path of G. So G has one neighbor that I can add. So I'm going to go down the path of F. And of course, I add G to the stack because I want to continue to explore G afterwards. And then I go down F. So I go down to E and I put F in the stack because I want to explore it afterwards. I go and explore D, and that means I put E in the stack. And then I put, I go down C, so I put D in the stack. And then the only neighbor of C that I can add is B. So I explore that and I put C in the stack. And then I see that B, I'm pretty much done exploring it. So I'm going to go back. Oh, I think I did miss F. It should be right here. So now I'm going to go back. I go back to B. So I'm back to C now. I try to see, are there any other paths that I can go to? I've explored B. D is already visited. So that's pretty much it. I have nothing else. I'm going to pop C from the stack. Then I'm going to go to D. Can I visit on any other paths from here? I can't, so that's pretty much it. Like I'm gonna pop D from the stack. So I backtrack back to D, and then I backtrack back to E. So I try to see, are there any paths I can explore from E? There aren't, so I'm gonna take that off the stack. I'm gonna backtrack back. So when I backtrack, it's basically the last item that was in the stack that I check. So I see that F is doesn't have anything else I can add. So I pop that from the stack so that now I'm back to G. I backtrack back to G. And then I see G, I can't add anything. So I pop that. And then I go back to H. And then I see H. I've already added A, G, and S. So I pop that. And then I go all the way back to S. And I see that all of F and B I've already explored. So I'm pretty much done. And now that the stack is empty, I'm done my DFS traversal. Okay, so that's one example of a DFS traversal you could do. Does that make sense? Time complexity for these are going to be O of V plus E. So basically, V is like the number of nodes, and E is the number of edges, right? Yeah, for both. So this is in an adjacency list. And for an adjacency matrix, I think it's O of V squared. Okay. So we'll go over adjacency lists and matrices. So for pathfinding, BFS would find the shortest path. Yeah, exactly. BFS is generally for a shortest path in an unweighted graph, which you guys have only been dealing with unweighted graphs. And DFS you can use to just find whether there is a connection between one node and another, like whether there is a path. And there's a lot of other things you can do with DFS as well. You can find out whether graphs connected. You can find out whether there's a cycle in a graph. There are a lot of things. So yeah. Yeah, BFS is basically just going level by level. Yeah, so V is going to be like the number of nodes, and E is the number of edges. So for both of them in an adjacency list, it's going to be OV plus E and OV plus E for BFS and DFS. Because you have to traverse through like all the nodes as well as all the edges, right? So for this example, like I guess it's kind of simple. Like you have just like these edges. You could also have like more edges, right? Like you could have an edge from like S to G, or like S to E, S to D. So you might have to actually explore like all these edges. But this example is not like that.
Just to quickly summarize what you said, so breadth first search is basically just that you queue up everything you're looking through, and then you use that queue to look through like all the possible connections. While depth first search is more like you're leaving a trail of breadcrumbs, and then once you reach a point, you're grabbing those breadcrumbs back and then starting from another point.
Yeah, that's beautifully said. I would say it's like that. Yeah, we'll go over some possible questions for OOP that I found from past exams, and you can probably expect similar questions. Okay. So I'd recommend to just do a little bit of practice, just like traversing through BFS, DFS, and just knowing how to implement DFS in particular recursively. I think that should be a pretty good amount of practice for that. So yeah, I showed you that traversal. I think in the solutions, I actually show you a different traversal. B squared is for matrices. Yeah. For adjacency matrices. Well, we'll get to it in a bit. So yeah, this is a different traversal. It's not exactly the same. I think This one I took things in a different order. Yeah. Yeah, because past exams are in Python, I think. So, and also they didn't really cover graphs that much. Okay, so let's talk about adjacency lists and adjacency matrices. So adjacency lists, to refresh, is basically you have an array, right? So like you have an array like this. Here it's vertically represented, where each entry is basically for the node. And each entry in the array is basically a linked list, which contains the indices of all the neighbors for a particular node, right? So here is an example of that. And these are straight from your Unit 5 slides, or, Unit 5 notes for PACO. And then adjacency matrix is basically, instead of having an array of linked lists, you have a two-dimensional array. So this is an n by n matrix where each of the rows represent a node, and each of the columns represent a node, and then each of the entries represent whether a particular node is connected to another. And it's 1 means that they're connected, and 0 means they're not connected. So a couple of interesting things is, if you actually read through the notes, is if you have an undirected graph like this one, fully undirected, then the matrix should actually be symmetrical. Like in this case, where you have 1 here, and then you have like 0, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, like that. So it'd actually be a symmetrical matrix. But if you have a directed graph, it might not be the case. So we'll go over an example of that. But more important thing to know about adjacency lists and adjacency matrices is the actual runtime of different operations in these representations. So this is again pulled from your Unit 5 notes. Edge query. So whether two nodes are connected in adjacency matrix, it's pretty simple. You can just do like matrix UV. Is it 0 or is it 1? That's just going to be a constant time operation. Okay, O of 1 just means constant time. But if it's an adjacency list, then what you have to do is, like, let's say I want to find out whether 5 is connected to 7. Well, then I actually have to go to the array at 5, and then I have to traverse through all the possible linked list items. And it's possible that 5 might be connected to every single node in the graph. In that case, every single node, remember that's represented by V, right? And so that's why we have O of V here, okay? Cardinality of V. So that's why that's that. Inserting a node, adding a new node to the graph. So in the case of an adjacency list, assuming there's space in the array of pointers to linked list objects, or these pointers are stored in linked lists, then it can be O of 1. And for adjacency matrix, it's going to be O of V squared. So the reason why it's going to be O of V squared is because if you insert a node, if you add a new node to the graph, you might have to resize the entire matrix, which means you need to add, since the matrix is going to be V squared, you need to add, yeah. Wouldn't edge query for adjacency be V plus E? I don't think so, no. Because E for a particular node can be connected to at most V minus 1 edges, whereas E is like the amount of edges for like the entire graph. Yeah. But V minus 1 is basically V and big O, because yeah, like -1 constant doesn't matter. Okay. Oops. Okay, so for removing a node, so basically it's O of E because the worst case scenario is like you have a node that's connected that is pretty much like the entire graph, like 8 to maybe like 7, 2, 4, 5, 6, 8, 9. Like these might be all the edges in the entire graph, and it's not, and none of the other things are connected to anything. So if you remove this node, you'd remove all the edges. So that's why it's going to be O of E. Yeah, and again, adjacency matrix is kind of similar reason. You'd have to shrink the graph. So instead of doing that, yeah, you'd have B squared. Yeah, so it's V squared for adjacency matrix because when you add a new node, so like let's say you have a matrix like this, right? When you add a new node, you need to like resize this matrix and like add a whole row and column. And so it would be V squared just to like remake the matrix. I think technically if you have like 100 by 100 matrix or something and you don't use up all the space, I think technically it wouldn't be V squared because you can just add like a node, for example, extra here. And then in that case, I think it would actually be O of V. I think it would be, but I would say just follow the notes that Paco has, which since the notes say V squared, I think you should just assume it's going to be V squared. But as always, like when you're doing big O stuff, you should always write what you're assuming, okay? Because your assumptions will ultimately decide like what the big O is going to be. Like here, we wrote that assuming there's space in the array of pointers to linked list objects. So this is straight from the notes. This is like an assumption that Paco's making. That's why we're able to say that it's going to be O of 1. Okay. So yeah.
The reason why it's OV squared for adjacency matrix is mainly just because when you add a node, you're technically adding another line and column. And because this is an assumption of an array, you kind of have to recreate the entire array with a new size, basically.
Yeah,
my understanding.
Exactly. Yeah, exactly. That's exactly why it is. Because you have a array that's a V times V array, right? V for each node. So you'd have to recreate that. Okay. So I'd recommend looking through the notes. So I'm just going to talk about these ones really quickly. So inserting and removing an edge. So for matrices, it's pretty simple, right? You can just change these to either 0 or 1, depending on whether you want to remove or add an edge. Inserting an edge, O of 1. Assuming new edge is inserted at the head of a linked list, then it's just going to be O of 1. So you have access to the actual node in constant time. So you can just add the edge in constant time if it's at the head of the linked list. But then removing an edge, again, you can access like an item, like 5, but it's kind of the same thing, right? So removing an edge is actually the same thing as just finding like edge query, whether they're connected. Like you have to go through the entire list to find where it is and then remove it. So that's why this is O of V. So yeah, just go over the notes really quickly. But I'm going to move on because we are kind of running out of time. Okay. Okay, so this is a question that I have found from one of the past tests. So it's pretty simple. The first part is just represent the following graph in the form of an adjacency matrix, adjacency list. So I'll give you guys like a few minutes to just sort of think about how it would look, and then we'll just take it up. For removing a node, wouldn't we have to check if any of the other nodes connect to the node as well? Actually, yeah, I think that is true. Removing a node. Oh, right, because then you have to go through each of the other nodes and then remove the edge. Oh, okay, I see. That's going to be, that's O of E plus V squared. That might be O of E plus V squared. You have a point. You have a point. It's interesting that the note said that. That's why it's O of E, right? Because you have to go through all the edges. Yeah, so I think E is always going to be greater than equal. It's going to be greater than equal to V. That's not true. That's not true, actually. No, not necessarily. Because you can technically have graphs that just have nodes and no edges. So in that case, actually, E would be less than V. Maybe we'll talk about it later if we have time. Okay. So let's just go through this really quickly. So this is just a graph that has these 5 items. So for adjacency matrix, what we're going to do is we're just going to set it up. So it's going to be index 0 to 4. So I've just like laid it out like this, A, B, C, D, E, A, B, C, D, E. But this is basically like 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, like in an actual matrix. Okay, so we're going to go through A, so column-wise. The whole row of A is connected to B and D. So therefore, B and D should be set to 1, and everything else should be set to 0. Okay, and then B is set, C and E is connected to, so C and E should be set to 1. Everything else should be set to 0. D is connected to E, C is connected to D and E. So those are set to 1, and the rest are connected to 0. D is actually, when I say connected, I mean outgoing edges. Okay, I hope that was clear. So these are like the outgoing edges in the rows. So D has no outgoing edges. And so the entire row for D is just going to have zeros. Okay. And then finally, E has an outgoing edge to A. And so this row is just going to have 1 for this spot and then zeros for the rest. Yeah. E22. Shout out. So that's pretty much how you do an adjacency matrix. You just set 1 to the edges that are connected, 0 to the ones that aren't. The left column is where the edge starts. Yeah. Yeah. For the sake of this problem, it says that you can assume that you have 0, 1, 2, 3, 4 representing these nodes for the matrix. Okay. And then let's talk about adjacency lists real quick. So you're just going to have an array, right? So I'm representing the array vertically like we saw in the example. And it's going to be basically a linked list here that's connecting all of the edges that are connected to a particular node. So for example, 0, which is A, it's connected to B and D. So we're just going to connect 1 and 3. Okay. And then you can end it with a null as well. Okay, and then B is connected to C and E, so we'll have 2 and 4. And then C is connected to D and E, so we'll have 3 and 4. And then D is not connected to anything, so it's just going to be an empty adjacency list. And 4 is connected to just A, so it's just 0. And yeah, if the connections were bidirectional, the matrix would be symmetric. But the connections are not bidirectional. Like from E, you have an outgoing edge to A, but you don't have the reverse back, which is why you don't have a symmetrical matrix. Can we write the letters that connect to each other? It depends on the question, I think. Like if the question says you can do that, then you can go for it. But typically in an array, here you have like 0, 1, 2, 3, 4 for the indices, and then you can represent each of the items as an index. Default is outgoing. Yeah. Yeah. Okay. So let's go over the next problem. So the next problem is provide a big O worst case complexity for the following algorithm. Okay, if it was implemented as an adjacency matrix or an adjacency list. So what this algorithm does is basically it goes through all the, so V is the number of nodes, E is the number of edges. So it goes through all the nodes, so I to V, and then J to up to I, right? So I can go up to V, but J goes up to I, so which means J is going to be like 0, 1, 2, 3 up to V as well. Actually, V minus 1 technically. And then this is edge operation basically checks whether this is true, whether an connection exists between these. So this is basically like querying. So in that big O table we saw, it would be the first entry. And then remove an edge is basically remove an edge, pretty self-explanatory. So I'll just go over it really quickly. So for the case of an adjacency matrix, so the first two lines are going to be the same for everyone. Okay, so line 1, you're going to do V iterations. And then for line 2, technically, you're not going to do V iterations all the time, right? You're going to do like 1 iteration and then 2 iteration and then 3 iterations. But if you remember from like A67, like if you add those all up, it'll end up being some factor of V, right? So this is also going to be V iterations. But then the is edge part. So for a matrix, does anyone remember how can you query? Or so what is the big O of like querying whether an edge exists in a matrix? Constant time? Yeah, exactly. So querying is going to be constant time. And then removing an edge in a matrix, I'll just say it, is also going to be constant time. Because removing an edge in a matrix is basically taking the entry, resetting it back to 0. That's it. So what you have ultimately is you have V times V and then a bunch of constant time operations. So it's going to be V squared, like Sean said. Okay. And then for adjacency list, so I'll go over it really quickly. So the first two are the same, but then for edge, for checking whether an edge actually exists, remember, you could put, since it's a linked list, you might have to go through all of the nodes that it's connected to. And all of the nodes would in that case be V. So that is an O of V operation. And then removing the edge, so according to the big O table, like we saw again for adjacency list, is also going to be an O of V operation. So what we ultimately have is V times V, and then these two O of V operations. So if you add these two O of V operations, you'll get that it's O of 2V. But as we know with big O, that's just going to be O of V. And so what you get is V times V times V. And that's going to be O of V cubed. So that's for running this operation on an adjacency list. Okay? So does that make sense to everybody? Why don't we multiply? So I'm guessing you're asking about lines 3 and 4. So this is not actually like a, so these are actually happening sequentially. Like this if statement, it's going to happen. It's going to, and then this line 4 is going to happen. It's possible that this line might also not happen. So the best case scenario is we just check and then this is not true. This doesn't happen. Still O of V though, in that case. It's because these operations happen sequentially. They don't happen within each other. So like for each check, for each of V iterations, you're not doing like a check. You're basically going through the whole thing V times, and then you're going through the whole thing V times again. So you're going through it twice. It's not O of V times, it's not V times V times V times V. It's V times V times V plus V. So that's going to work out to be O of V cubed. Okay. Yeah, if you want like explanation about this, you can also just email me. So I'll just write my email. I know there's no more office hours, so feel free to send an email to me over the weekend if you have any questions about that. But I'm going to move on to this last little part, which is not going to take too long. It's just going to be about object-oriented programming. So this is just to give you guys an idea of like what kind of questions you could get. Is edge part redundant? I think it's required. It's part of the question. Yeah. So for object-oriented programming, there are different fundamental software design principles. So one of them is modularity. So this is just like one of the questions that I saw from past tests. You could get asked about like the other possible software design principles as well. So I'd recommend going over those definitions and understanding what they mean. So modularity is like the whole idea of splitting a program into individual models. And each module does one thing very well. So you don't have one module trying to do many things very well. And the question specifically was, what are the benefits of modularity? So for the sake of time, I'll just go over it really quickly. So some of the benefits of modularity is reducing the repetition of code. Then improving the chance that the code you write will be reused. And then making it easier to test your code and verify it's correct. So like these make sense. If you have code that is very modular, it's very easy to test. I think that's like the biggest benefit. If you have a lot of operations being done in one module, it can be pretty difficult to test. So that's pretty much modularity. I'd recommend going over the other design principles as well. And then, yeah, I guess another benefit is it helps you see the big picture of how your software is structured and how it works. I mean, I don't know if you have to give like 4. I just gave the ones that were in the lecture notes. Okay, and then there's a concept of good APIs. So what are APIs? So application programming interfaces. So they basically settle the details of how modules communicate and interact with each other, and they contain like the specifications to make use of interact with different softwares. So examples of this is like Google Maps, TensorFlow, Amazon AWS, Unity, the engine, stuff like that. And so a question in this test was, what are 2 properties of a good API? So if you remember from looking at the notes in particular, we talked about some things about good APIs are like they're easy to learn and use, and they're also difficult to use incorrectly. They're easy to maintain, so they're readable and they have well-written code, and they're easy to extend and improve. And there are also some other benefits too if you look into the notes. So those are just some. It only asks for 2. Okay. And then finally, like another example of an object-oriented programming question is like C++ versus C. So you don't actually need to like know how to code necessarily like super in depth in C++, but you should at least know what are the major benefits of using C++? What are the things that we can do in C++ that we aren't able to do in C? Okay, so one of the things is you can set private and protected variables in C++ explicitly. C doesn't explicitly have a way to hide encapsulation. there is technically a way to like feign like private variables, like approximate the behavior of private variables in C, but I'm not sure if you actually learned it. And plus, it's not as robust as in C++. It's not as robust, or it's not as well designed as it is in C++. So information hiding is like a big thing. Encapsulation. And then also another thing is method overloading. So being able to define the same function or method, but have different parameters, right? So like, for example, a graph, I think this is exactly in your notes, but like being able to set up a graph using an adjacency list versus setting up adjacency matrix, right? In an object-oriented programming language like C++, you could have like two different methods that with the same name that accomplishes that handles different data types. And then another thing you can do is also polymorphism and inheritance. And yeah, so that's like another thing you can do. Just the whole idea of like being able to inherit from classes and being able to deal with multiple, in a function, being able to deal with multiple different data types and being able to do functions in them. So I think that's pretty much all the content we wanted to cover. So if you guys have any questions, feel free to stick around for a little bit. But other than that, I think we're pretty much done here.
Yeah. There was a little bit that I wasn't able to cover. There's 3 questions that were on a previous exam that I didn't cover. So I don't know if anybody wants to go over it. I'm free for the next like half an hour-ish. And like I will go over it if people want to. Yeah, it's from last year, so it's relatively recent. Yeah, okay. It'll be like a long thing, but yeah. Just for the sake of time, like I want to respect your guys' time as students, and I've also got an exam tomorrow. I'm not going to go over the sorting algorithms. They're on there. They're on the slides, like the algorithms to actually code for quad examples specifically. But yeah, let me share my screen first. Gotta love Captain America quotes. Okay. Let's see this. So yeah, as you can probably see, like in order, traversal, quad, and post. But this is what we want to go over. Okay. So this is one of the examples on a previous exam. So we're going to code over sum to depth. So we're going to use this BT node. No, it's not a BST. So it's not organized. You can add helper functions or additional parameters. Your code must be recursive. So they'll explicitly say that on an exam if you need it. Yeah, okay. So for this one, sum to depth, basically it's giving you like 3 parameters. You're given the head of a BT, the depth to which you want to get like the sum of all the different numbers for the data, and then the actual depth. So the depth always starts at 0. Yeah. Root is at depth 0, and it's less than or equal to n. And yes, I will resend the slide link. Okay, so for here, first thing to make sure, your BT node is not null. Otherwise, you just want to return 0. Then if we have found the depth limit, we actually want to return the data. And then from there, we want to keep recursively calling this. So we're going to find the data of the current node plus the sum to depth of the left one and the sum to depth right. Now you'll see this plus plus. That's kind of important. It means that you're going to pre-increment the number. So what that means is if you do depth plus plus, like what you remember back from Python A08, that'll do a post increment, which means that it'll add 1 to depth at the end of it. So, exactly. So since we're adding 1 at like before, depth already has +1, and that's why I don't do it on the right side. Because if you do, you're adding 1 twice. So basically adding 2, and that's incorrect. Yeah. Yeah. I don't know if you could use tail recursion. I think you could. Yeah, okay, so I'll re-explain it. So basically, yeah, I think it is tail recursion. Basically,
it's not tail
sorry.
recursion because you're doing an operation after you finish, which is all the adding together. That's not tail recursion.
Oh, never mind then. Yeah, okay. So basically you are going to the depth in the BT tree, or like the binary tree, and you're adding all of the nodes data together, basically. Yeah. So you'll check whether or not you found a leaf node. If you have that, or like if it's empty, like left and right nodes, whatever node you're at, you want to make sure it has data so you can access it. Then if you found the depth that you want to stop at, you just return the data. Don't actually go and keep adding the left and right nodes because those are child nodes and you'll overextend your depth. And then last but not least, yeah, so you add the current node's data to the left side, recalling this, you add 1 to depth, pre-incremental, and then you add the right side. And since depth has already been added once, then that means that you don't have to increment it again. Yes, Sean?
So when we do the first call on the last return statement, the kind of beefy one, will depth be 0 and 0 for the first call of these two functions?
So the first time you call it, yeah, first time you're gonna call it, you're going to add like t at data, like the depth will be 0. And then as you keep moving along it to the second one, the first call of sum to depth will be added, like 1 will be added to it. So depth will be equal to 1. And then when you call it on t to the right, it'll also be 1.
So on both it'll be 1.
Yeah.
Okay.
Because you've added 1 at the beginning. If you add it like twice, then technically depth will be equal to 2 on the second one, and that'll be
So
incorrect.
if we go 1 line above the one that we were talking about and put depth plus plus, then we can just
That'll
put
be
depth
fine.
and depth for both, right?
Yes, exactly.
Okay, it's the
this
same
is just
thing
a
then.
fancy way to do it. Yeah.
Yeah,
I
it's
just
basically
wanted
like
it on
there's 2
one
lines
line.
in one thing. Okay, I understand. Thanks.
Exactly. Yeah.
So it equals
So-
to we call on depth plus 1 for twice, right?
Sorry?
Just like I sent in the chat, if we want to do recursion without the plus plus, can we do like depth plus 1 for the left sum as well as depth plus 1 for the right sum?
I think that'll work. I think it will, yeah. Just don't do plus plus, because the plus plus is called specifically post increment, which means it'll add it after it already executes the function. So technically the first time, like on the left side, depth would be 0 if you did depth plus plus, and the second one would have depth plus 1, or a B1. It might be indented. Honestly, it's yeah, don't worry about indentation. This was just like copying and pasting from my like Notepad++. But yeah, it probably should be like 1 more behind. Does that make sense? Does everybody understand this? Good thing it's not Python. Yeah, no kidding. Yeah, honestly, I prefer Python. No offense to C. C is a really low level language. Okay. I'm going to assume there's no questions. So the next one, we're going to be looking for biggest internal. So basically, we're just trying to find the biggest number of data that's not a leaf node. It's not stored in a leaf node. I mean, what? No, C is wonderful. C is beautiful language. I get to make music with it. That's fun, actually. Yeah. So what we're gonna do here is we're actually gonna make a helper function. So we're gonna call it leaf. Make sure that you import std bool, because bool technically isn't already added in here. So yeah, that's why I did at least. So you import it or you include it. We create a function, a helper function, to determine whether or not a node is a leaf. Yeah, Joseph?
Just out of curiosity, couldn't you just do 1 or 0? Because if I recall correctly, if statements also read 1 or 0 as like true or false as well.
You can also do that, yeah. I just wanted to use Booleans. Yeah. Just for like ease of readability, right?
Understood.
Yeah. Yeah. Okay, so for this one, really simple. If it doesn't have any children, it's a leaf. And if it's empty, it's technically a leaf, but like it's no. Yeah, sorry, that should be and. Sorry, that's a typo. Yeah. Otherwise, you return false. If it has a child or it has 2 children, then you want to return false. So as you go through, if if the head of your BT is just a leaf node, then just return -1, because that's an error. You cannot have a leaf node. I'm confused by the numbers in the chat.
You're just making fun of the fact that some people mark harsher than others. So if you have like 1 and, you get -2, -5.
Oh my god, guys. Okay, fine. Yes, there's supposed to be an and there. I do know that. Yeah. Yeah, okay. So temporarily, we're gonna have the biggest value. So I get the value of the node that we're looking at. And if the left is not a leaf, then find and compare the biggest internal in there. So this is the recursive call in there. And we compare it right there, right then and there. We do the same on the right side. So you want to make sure first the right side is not, right side is not a leaf. And then you go through, you try to find it. And then at the end, you return val, or you can rename it as you please. Yeah. Any questions about this? I think it's okay. Right? You're just trying to find the biggest value in a BST or a BT technically. If it was a BST, it would be really simple. You just keep going to the right side. Kind of like the opposite of finding a successor. Yeah. Last but not least, this was kind of a weird one. But this is called set parity. It was on the exam last year as well. So for all nodes in the BT T, the binary tree T, if the node is a left value, set it to -1. If the node's a right child, sets value to 1. And if it doesn't have any parents, which is just the head, set its value to 0. All right, so if there's no BT, you just return. Also note that like the return value of this is void. You are just resetting all of the different values inside a BT. So default is 0. Specifically, if you're starting off, T is the head of the entire BT. So make sure that you set T equals to 0. Then you're going to go down the left and right first before you evaluate like what the actual one you're looking at is now. So you go down the left and right side, right? And you set them all equal to 0. Then, if you have a left side or a right side, overwrite that data. So whatever was in there, if it's a left child, set it to -1. If it was a right child, set it to 1. And then you return, you keep going up the tree. And I believe that's it, yeah. You could also, yeah, you could say if it doesn't equal null, yeah. So for clarification, yes, you would want to say if it doesn't equal null. The way, like Tabeb, correct me if I'm wrong, but I think the way that if they evaluate Boolean values like null, 0, empty, empty string, all of those evaluate to false, so to speak, or 0. So by saying if T of left, or like the left one, just that, it's just asking, does it have something that's not equal to a null value, like null, 0, empty string, etc. Yeah, it is implied in C and Java. You'll learn later on in B07. But for clarity's sake, probably put the not equal to null.
Just to explain the recursion part, what she's doing basically is that she's calling the set parity again in order to clean up all the data below it. And once all that recursive calling is done, then the data will go from the bottom and up and build on the data and do a 1 or -1 if it's a left or a right node.
Yeah, thank you, Joseph. Exactly that. So all of the data will be equal to 0, and then you start overwriting left or right.
So we're going to the left and right children for each node and then setting them to 0, right? That's the effect that both set parities have?
Yeah, so you go all the way down to the bottom. You set all the values equal to 0, right? Because that's what you're doing here, then go left, right. Set it left, right. And then once you get to the bottom, you start working up. So then if it's a left one, if it has a left child, set equal to -1. You're overwriting it as you go up.
Okay, I understand it conceptually, but tracing recursive functions for me has been really hard. So do you think that you could help me understand this?
Yeah. Okay, 1 second. So there's something really cool. There's a website that I will post in the chat. Oh, I gotta find it. 1 second. It's binary search tree visualization. It's a really useful website. I use it all the time to visualize stuff. But one thing that it does do differently than what we teach you is that if it's equal to it, it goes to the right side. And if you are deleting a node that has 2 children, it takes the predecessor. So instead of the successor going down the right side and then finding the smallest value there, it actually goes to the left side and finds the biggest one from there. They do basically the same thing. It's 2 implementations that they both work. It's just based on preference. Yeah, I hope that helps. But let's try to go through this. So let's say we have. Let's start with like some easy numbers. I'm just inserting random numbers, don't worry. Like these have no significance. Also to answer France, when I say if t of left, or like t's left, the left child, I'm seeing whether or not it exists. So if it equals 0, then yeah, I'm basically checking if it's not null. I would put if not equal to null, if t of left is not equal to null. Put that specifically just because if the data is equal to 0, technically it exists, but my function would not return that. Okay, so we have this balanced tree right now. Oh, actually it's a, okay, so this is BSTs, but technically this question is asking for BTs, so we're gonna have to go through the entire list anyway. So let's start at the top. Let's say we're setting the parity. We set T, actually I can separate this. So we're gonna set, let me see if I can, I can't zoom. Is there a way to close this? Yeah, okay. So let's say we're going to set T to 10, right? So first thing, T is not equal to null. So we're not gonna return. We set T equal to 0, its data equal to 0, okay? Then we're gonna go down the left. So let's first go down the left and recall it. One way to visualize this is if you actually draw it out, you can say still waiting on like set parity T is right, and then the 2 ones down below. So now we're moving to recalling it, set parity T of left. So now T is equal to the node with data 5. So it's not equal to null. We reset this now equals 0. Actually, yeah. 7, that's a great way of putting it. Pre-order is going all the way down. We're setting everything equal to 0. And then we have this recursive call where all the calls are stuck at the bottom. Okay, and then at the bottom, we go back up, just like post order, and we overwrite all the different 0 values. It's kind of a combination of both because you're setting the data equal to 0, first of all. You're going through all of them, rewriting them to be 0. Yeah, so it is a mixture of both. All right, so we're at 5. We set it equal to 0, and then we go down the left again. We go to 1, it's not equal to null. We set it equal to 0, and since if we go left and right, both of those are just going to return because they're both null. This is a leaf node. So from here, now we're going to say if T of left, there is no T of left or T of right, so then we just go back up. So now we're at 0 or 5. What it used to be 5, but now it's 0. Since we went down the left side, now we're going to go down the right side. So same thing. So right now 1 is now 0. 7, we go left and right, they're both going to return. Exactly. 0, 0, 0, 1 has data 0 right now. We're not finished though. 0, 0, 0, 7. What we do is we go down the left and right. They both have null. And then it doesn't have left or right, so then we return. So both 1 and 7 have data of 0 currently. But we haven't finished 5. So 5's execution has gone down left now, has gone down right, but now it's going to overwrite the left and right values. So since it does exist, the left child is not null. We're going to set its data, overwrite its data that was 0, and now it's -1. And now we'll also do the same thing with the right, except now the right child's going to have 1. Yeah. And then now that that's done, even though 5 still has data of 0, when we go back up to the recursive call of 10, it's going to overwrite the same way. Left is going to be -1, right's going to be eventually 1 once we go down the right side. Yeah. Does that help?
Hey, do you think that you could explain the going back up bit where we set either -1 to 1? I think I kind of missed the important bits.
The -1 to 1. Okay, yeah, so did you understand the 1 and the 7, the data being overwritten of the 5?
No.
Okay. No, it's okay. It is quite confusing. Let me see if I can. You know what, let me pull up Notepad. Or no, not Notepad, just Notepad. So let's say we're going down this, right? Okay, we got the code, we got the picture, we're good. First recursive call. We're gonna start at node 0010, right? We're gonna reset its data to be 0. And now we're gonna go over to the left. Go down left. Okay. Second recursive call has now just started. We're working at 0005, or I'm just gonna say like 10 and 5. Data is now reset to 0. Go down left. We might be able to do it with in order. I think so. All right, third recursive call, right? We're going down the left side right now. We are now at node 1. Data is 0. Take care, everybody who's leaving, by the way. Good luck on your exam. Yeah, I think any traversal, it's honestly preference. So now that we're at number 1, we're looking at the left and right, and they're both empty. So we would still go down the left, but this would result in like just a return. Go down right, return. Since the left and right don't exist already, like for this last time, we don't overwrite anything and we just return. So the third recursive call is done. Now we go up to this 5th one. So we've done the go down left. That led to the third recursive call, right? Now we're going to go down the right for the second recursive call. Hopefully this is helping. Yeah. I think Ethan's got a really good point. If you have, like if you do another order traversal, like in order or pre-order for the final things, you might end up overwriting things with the wrong value. All right, so from the second recursive call, we're at 5. We're going down the right. This is technically the 4th recursive call. So from here, we're looking at node 7. Data is set to 0. Go down left and right. They both return, and then it returns.
Hey,
Is this...
just a quick question. So when we do recursive calls, in a situation like this, let's say we're at node number 5, right?
Yeah.
So it's evaluating like what's going on in node 1 and 7 at a similar time. I'm not sure how to phrase.
It's okay. So it's going down like each line. So it starts with left, and then it keeps like it stops the execution for the 5th node until the recursion is done. Then it'll go down the right side, which will be the next recursion call. And then once it's done both of those, then it'll actually execute at 5. overwriting the left data and the right data.
So I'm just gonna draw on the screen really quickly. We go from here to here, and does it then go from here to here and then back and then here?
Yes, exactly.
Okay, so it's not something like here and then here and here.
No, it'll go
No,
down
okay.
left and then it'll return and then it'll go down the right. So it'll go back to the fifth. Yeah.
Okay. Yeah. All right. Yeah, that clears up a lot actually.
Yeah. I hope if you have any other questions, let me know. I can also send my email in here. If anybody has any last minute questions, for graph questions, ask Tabeb. I haven't really gone over graphs in a while, in like DFS and BFS. But if you have anything about BSTs, or recursion, yeah, let me know. Yeah.
All right.
Yeah.
I think that's pretty much it. We've been going on for more than 2.5 hours, so I think I want to give you guys a break. And if you guys have any questions, again, I've sent my email, so you can send me emails. Other than that, we'll post this recording on Piazza once it's ready. And yeah, good luck everyone on your exam. I'm sure you will all do great.
Best of luck, guys.